Hello, friends. Welcome to Science Talk. I am your host, Jim Massa. In this video, I wish to address a comment left by one of in our Patreon community. Heather asked me if I could elaborate, expand upon a comment I made in my ocean heat content update video as to um, my assertion that the planet is locked on a trajectory of warming of 5 to 11 C by 2100. And I'll be quite happy to do so. So here we go. Well, let's first of all, what we know. We know that CO2 is, as it increases, the temperature increases. We also know that tends to be a lag effect, so that what we are experiencing now is really the result of CO2 levels from 10, 15 years ago. And that current CO2 levels will not be felt until 10, 15 years down the line, approximately. So we know that. And so the current levels that we have currently in the atmosphere, the effects of those are still to be felt and will not be done so until 10, 15 years from now. The other aspect, of course, is that as we increase the temperatures, that increase the rate that the permafrost thaws at. And so we're now measuring considerably methane and nitrous oxide uh, levels are increasing. So that overall, the CO2 equivalent levels are increasing. And as they increase, temperatures further increase. And we're now seeing that this is taking place exponentially. Another aspect is that the Arctic region, the Amazon rainforest, oceans have long been carbon sinks. And now they are no longer carbon sinks. They're becoming carbon sources. This is huge, and this is helping to add to the ever increasing uh, CO2 equivalent levels, the ever increasing temperatures that we are measuring in the Amazon forest, right, and elsewhere. But humans have been what, cutting down trees, burning the ground, slash and burn kind of agricultural practices, for example. All of these do what? Add CO2 to the atmosphere. And when you have grasslands do not draw down as much carbon as do trees, heavily forested trees. And we are seeing more and more fires. Well, fires burn biomass. When they burn biomass, you guessed it, CO2, more of it is released. And then we have, of course, ocean heat content, which I have shared with you. And we're seeing what? That the heat is diffusing to the atmosphere. It's diffusing to the atmosphere because the sequestration of heat and carbon, for that matter, is no longer taking place. So we're not like scoring it away and forget about it. No, the heat is staying in the upper levels. It's diffusing to the atmosphere. As the heat diffuses, so does CO2 that may be dissolved in there, further increasing the CO2 level, further increasing temperature levels. We know that gas solubility decreases with an increase in temperature, adding further CO2 to the atmosphere. And don't forget, as we're heating the ocean, we are stratifying the ocean, further inhibiting sequestration of heat and carbon to depth. So, in essence, we're setting up really a double whammy here. We're having the CO2 from the continuing burning of fossil fuels and the oceans are diffusing, fluxing, if you will, uh, heat and CO2 to the atmosphere. So it is fluxing the CO2 and the heat from the oceans to the atmosphere, further increasing the CO2 level, further increasing the warming. You can see now how all these things, and I'm not done going through all the parameters here, how all these things are helping to exponentiate what we are seeing, to accelerate the warming. These all work together to accelerate the warming. We know that warmer air holds more moisture, right? I shared with you how for every uh, approximate 1 degree increase, 1 degree C increase in temperature, uh, rain events or precipitation events increases by about 7%. The intensity of it, the amount of moisture that will be held, increases by that amount. But here's the other thing: if you're increasing, the ability of the air to hold more moisture, if you have dry regions there, it's going to do what? It's going to suck the moisture out of the ground, putting at risk the ground to burn up later on. And this is what we see happening. For example, look at the fires in the Arctic region, like Siberia, Alaska, a couple of years back, Scandinavia. We've seen that. The permafrost in some places are drying out. I've noticed that just walking around here on the permafrost, used to be, soggy and boggy, squish, squish, squish as you take your steps. Now it's crunch, crunch, crunch because the permafrost has gotten so dry. It's really very troubling. And another thing, water is a greenhouse gas. You increase the air temperatures, right? You increase, we just said that, water content in the atmosphere will increase. Now, here's another thing. When you burn alkanes, they say hydrocarbons, alkanes are hydrocarbons containing only carbon and hydrogen, and every carbon is a single bonded carbon to every other carbon, no double bonds or triple bonds, anything like that. And when you burn alkanes, combusted with oxygen, and alkanes is gasoline, come to mind, right? Propane. When you burn such substances, the products are not just CO2, but H2O, water. So when you burn fossil fuels, a lot of the gasoline, the propane, you are creating not just CO2 adding to the atmosphere, but water vapor as well. Just take a look at a tailpipe. Drip, drip, drip at the end of the tailpipe. That's water. And we know that it's not just temperature, but temperature and humidity. So the CO2 and the water vapor work synergistically together to actually increase warming effects. So, there's also that. Trees are stressed out nowadays because the temperature has gotten warmer, and trees, plants in general, like every other organism, have preferred temperature ranges. And right now, the temperature ranges are beyond their preference. So instead of photosynthesizing, a lot of them are turning to respiration. And by doing so, the respiration is doing what? Instead of drawing down CO2 as in photosynthesis, and creating oxygen as a product, it's drawn down oxygen and puts out CO2 as a product. So we're seeing decreasing levels of oxygen, and because the trees are stressed out, they're further adding CO2 to the atmosphere. This is startling. Not to mention what this does, basically what we're saying is that productivity is decreasing. Warmer oceans, right? I've shared with you many videos how the warmer oceans spreading out over shelf regions, especially in the Arctic, is helping to thaw out the permafrost that's found there, releasing whether it's biogenic or thermogenic methane sources, increasing the methane. And we already know about the permafrost dying out, right? So we're doing all these things to increase the CO2 equivalent level. And remember, methane doesn't go away. It oxidizes the CO2, so its effects are still felt. When you have the warmer seas moving into the Arctic Ocean, melting the sea ice, preventing the sea ice from forming in the first place, so that we have longer and longer seasons of open water, we're doing what? We're decreasing albedo, increasing absorption, warming up even further. I touched upon briefly stratification, right? So we know in the oceans. So, this of course prevents, sequestration. But the other important aspect of this is the decrease in primary productivity. So we're seeing a decrease not only from terrestrial plants being stressed out, but when you have continual or near permanent stratification in the oceans, primary productivity will decrease. Now, it's important. You do need stratification in order to get the productivity to take place. And productivity tends to be seasonal or an episodic events. But in order for the productivity to take place, you need a vertical mixing of the water column to mix the nutrients into the photic zone. Then the stratification basically locks in those nutrients in the photic zone so the phytoplankton can go do their thing, and then you have the zooplankton feeding on the phytoplankton, secondary, tertiary productivity, and so forth. But the secondary and tertiary productivity cannot take place unless you have primary productivity. And if you have in a state of the ocean that is basically almost permanently stratified, eventually the nutrients are going to run out. It's a reason why most of the productive waters on the planet are mid to high latitudes, because you get this turbulence, if you will, you get this mixing and so on. You go to the tropical oceans there, you have a near permanent thermocline, and so not much productivity takes place. Other areas that are really productive are, basically areas over the continental shelves where you have Ekman pumping, transporting nutrients up onto the shelf that the phytoplanktons gladly utilize. The middle of the ocean, the gyres tend to not be highly productive regions at all. But so we have the decrease in primary productivity. This will, of course, lead to a food chain collapse. But here's the other very important aspect. Phytoplanktons provides 55 to 80% of atmospheric oxygen. If the phytoplankton start dying off, what do you think is going to happen to atmospheric oxygen? And by the way, we're measuring a decrease of that. So in conjunction with the terrestrial plants switching more to respiration, we also have phytoplanktons releasing less oxygen to the atmosphere, so that we are now measuring a decrease in atmospheric oxygen concentrations. Extremely troubling. And of course, we know that with the warming ocean, then of course the increased CO2, you have acidifications of the ocean that threaten organisms. We see, for example, the CCD, the calcite compensation depth, is getting shallower and shallower. Basically, below the CCD, and that transition is called the lysocline, but below the CCD, calcite, aragonite, whatever, but the general forms of calcium carbonate tends to stay in solution. Either increased pressure helps keep it in solution. Also, increased temperature tends to keep things in solution. But the CCD is getting shallower and shallower, so that, as I just said, below the CCD, calcite tends to be in solution above it, it precipitates. There are many organisms that utilize calcite to make their shells, make their tests. If the CCD gets shallower and shallower, these organisms are not going to be able to make their shells, make their tests. There, there will be increased mortality. So that's something else that is taking place. In essence, when you look at what all that's going on, and then you throw in human overfishing and so forth, and decrease oxygen levels because the oceans are warmer, so that organisms such as the marlins, the tunas, the great white sharks, which are all homeotherms, uh, so they have a higher metabolic rate, requiring a higher oxygen intake. They are all placed at risk. So, and then of course, we're overfishing, and all these things are going on in the oceans. The oceans are, to be blunt, dying. And if the oceans are dying, we are dying. So everything that I have mentioned thus far to this point, all these different parameters, all lead to basically a whole pile of positive feedback loops being set up and kicked into place. And so that this is leading to exponentiation of the CO2 levels or CO2 equivalent level, the warming, and with all the adverse effects that those bring, such that things are accelerating. And think of, to use physics here, you have your position function, you take your first derivative, it's velocity. Well, then if you change in velocity, it's called acceleration, typically the second derivative. Things are accelerating. So when a lot of these research, especially IPCC, are assuming linear increases, they're basically saying there's no change in velocity. There's zero acceleration, and that is, as I'll mention later on, and that's an error. Right? So things are accelerating. The exponentiation itself is accelerating, and at some point there's going to be, and we're seeing it, and at least in some of the parameters, there's going to be a change in acceleration. So when you hear me say in past videos that the exponentiation itself is exponentiating, that's a change in acceleration. So the acceleration is no longer constant, but in itself accelerating. In fact, it's a third derivative. We call it the jerk. Think of the scene from I think it was Apollo 13, when one of the rocket stages gets used up, and then the next stage kicks in, and you see the astronauts basically going forward in the seats, and then boom, and they're shoved right back into their seats. That's the jerk. That's why it's called the jerk, because of that rapid change in acceleration, and things are accelerating across the planet. Everything we put in motion is now accelerating. Now, I did a video some couple of years back, and the video is called "Lessons from the Early Eocene." And you may want to go look at that again, because I'm basically, and this is 2 years ago. I'm still, even then, I was laying out what's a lot of the things we've just been discussing of what's going on. But in this video I shared with you, I was talking about a paper that appeared in the journal of Science Advances, where the PI is Christopher Paulson, associated with the University of Michigan, along with Jessica Turney from the University of Arizona. And they basically, in their modeling, they assert that we are on track to, at minimum, a 5-degree C increase in temperature by the end of this century. There have been other papers that put the range from 5 to 11 C. So now you see where I got those values from. And I'll talk about this a little more detail later on. But what they did that was different was they took into account water vapor and aerosols. And so I'll have more on that in a bit. We're now seeing, that the IPCC is wrong to keep using linear models, so that the result is a woeful underestimation of what is happening. As I just mentioned, things increasing exponentially, and now they are ramping up, such that things are accelerating, so that the exponentiation is exponentiating. That is wrong. And the other problem with the models, you've seen the graphs there. You see the projection, and you got these different types of models with the different types of outcome, and a big, huge, wide range of that. A big error in what they're doing is that they're assuming humans are going to implement greenhouse gas reduction measures. We don't know if humans will do that. I mean, everywhere you look around, increase fracking, build some more coal plants. I mean, it's just, we can't assume that. So those are erroneous assumptions. And then they go with the linear models, and basically the models are shit. I'm just going to be blunt. They just do a poor job of it. So that we're now seeing more and more researchers, if they use any of the IPCC models, they're using the RCP 8.5, basically the worst case scenario model. So why are they doing that? And I'm seeing more and more papers looking at using that one to examine. Why? Because that's what the data is indicating to us, the worst case scenario. So when you take together all the things I have mentioned, the trees stressing, the fires, increased temperature, increased CO2 equivalent levels, outgassing from the ocean, all these, everything I just mentioned thus far to this point here, that a 5 to 11 degrees C increase is not unreasonable. And that's basically halfway, 2/3 of the way to the PETM levels, right? The Paleocene Eocene thermal maximum of some 56 million years ago. And here's the difference: we're increasing this in a couple of centuries versus tens of thousands of years, as it took place 56 million years ago. And by the way, there are many population scientists, biologists, who basically state that an increase in temperature of about 4C is sufficient to cause human extinction. And it's not going to be like, if things have warmed up 2 degrees, things have warmed up 3 degrees, 3.5, 3.6, 3.8, 3.97, 4, and we're all dead all of a sudden. No. As the temperatures keep increasing, the mortality will keep increasing, because also what goes with that is the loss of cropland, so that crop yields are decreasing, the nutritional value of the crops decrease. I've covered these different aspects with you before in the past. We're going to create climate refugees, because some places will become too intolerable to live in, whether it's excessive flooding or excessive drought, excessive fires. We're going to create climate refugees, whether it's North America or in the Eurasian landmass. It's happening now. The projections that the Middle East will become inhabitable. And if you look at what's going on the west coast of North America, on the western side, that's becoming inhabitable, to be quite blunt. So we're going to be creating all these, we're changing everything, and we're going to create climate refugees. I haven't even yet mentioned the effects of sea level increase. Yeah, sea level is going to rise, and the low-lying areas are going to be flooded. There's more climate refugees, but it isn't. But sea level rise is not going to just restrict itself to coastal areas. If you've got big river drainage systems, such as the Mississippi, the Amazon, right? Those places there, the water is going to move inland. It's going to create like an inland sea. North America has seen that before, like during the Jurassic era, where New Mexico was beachfront property, because we had this huge sea basically bifurcating, or not bifurcating, but bisecting the North American continent. And with the sea level invasion, you're going to what? It's going to get into the groundwater, making the water non-potable. And if you have crops that cannot tolerate salinity, guess what happens to the crops? So we're going to be creating. So all these things are going to create mass starvation, and then people are going to be, stressed out and fleeing for their lives, what have you. That leads to tensions, and humans being a violent species that humans are, you're going to have the increased risk of wars. And if you got infiltration of, of brine into the water tables, it's not going to be drinkable water, so there'll be wars fought over that. So a war could, wipe out human, and this war will have been the result of what we've been doing, burning the fossil fuels, all the changes we've done to the biosphere. So you have all that, and of course, factors leading to the sea rise, thermal expansion, melting of the major ice sheets, and so on. But that's another factor to take into account. So, when the ecologists, population biologists, state that an increase of 4C can lead to human extinction, that is, sad to say, not unrealistic, and it's extremely sobering. I mean, if you look at the IPCC, they're saying right now 1.2. Look at all the damage 1.2 increase has done. But consider the fact that the oceans have absorbed 93% of all greenhouse gases since 71. So look what that other 7% has brought and wreaked upon us. And I'll get to that point right now to build on that, is that all this heat energy in the ocean, even if only 1/4 of that diffuses to the atmosphere, that's enough energy to increase temperatures by around 2, 3, 4 degrees C, in addition to what's happening. Well, it's taken, in fact, all the other aspects I've discussed with you. And we know that this heat does eventually make its way back to the atmosphere. So when the ocean is drawing down the heat, that's just a temporary respite. So let's throw some rough numbers out here. Since 1971, approximately 270 zettajoules of heat energy has been created by humans burning a fossil fuel. About 240 of that has gone into the oceans, right? Approximately. So the other, and these approximate numbers, I just rounded it off just to give you a ballpark figure. So everything that we're experiencing, everything we see across the planet, it's basically the result of 30 zettajoules. And we, look what that has done. So if we just say 25% of that 240 zettajoules that's in the ocean, and that diffuses, fluxes to the atmosphere, it's about approximately, say, 60 zettajoules, right? That's enough right there to guarantee an increase of at least 2 degrees C, if not more. And what's to say not more of that energy diffuses back. I'm being extremely conservative here, just to illustrate the how dire the situation is. Now, since 1971, right, this is what a lot of these values are based upon: ocean heat content, absorbing 93% of fossil fuel heat, and so on. So since about 1971, we've seen a temperature of about 0.8 C increase. Here's an example that exponentiation accelerating. If you go back to 1750, the temperature increase is really more like 1.6, 1.65 C. So why do we see 1.2? Because the IPCC keeps moving the goalposts. First the baseline was 1750, as it should be, because That's pretty much when the Industrial Revolution um, started. The birth time of it. Then they did what? Oh, 1850. We'll compare it to 1850. That's when we see the big, huge increase in factories, for example, in England and so forth. And now let's compare it to the late 1880s. And when they do that, oh, it's only 1.2 C increase. Well, I'm sorry. Changing the science, changing comparisons like that, or changing your baselines to make comparisons is simply, you're changing the methodology, is simply shit science. That's just poor science. You don't change them, especially when you're doing comparisons, you don't change the methodology. Now, you could say, well, since this time period the increase is this much, and as a subset, a sub-analysis, okay, fine. But in the overall picture, if you're going to state 1750 is the baseline, and for these reasons, valid reasons, yeah, then you stick to that. You want to say, all right, overall, it's this amount. Since this time period, we see the increase is this amount. That should be indicative of the severity of issue, how things are exponentiating. So if from 1750 to now is about a 1.6 increase, say, and from 1971 to now, we've seen a temperature of 0.8. That means in the last 50 years or so, we have seen half of the overall warming. So from 1750 to 1971, a period of 221 years, temperatures increased by half a degree C. And then 50 years, 1/4 the time, we've doubled it. Tell me that isn't exponentiating. Tell me that isn't an exponential increase. So now the question becomes, why do we see this range in the projections of how much warming will occur by 2100? Now, why the range from 5 to 11C? Well, there are two major aspects. Let me start with water vapor. Water vapor is a very difficult parameter to model. It's hard to do because, say, for example, the top of clouds, and clouds are water vapor, right? The top of clouds, you have a higher albedo, it reflects sun energy back into space. So that has a cooling effect. The bottom of clouds has a heat trapping effect. So you increase temperature. So you have to look at the net. Is there net cooling or net warming? And then different clouds act differently. Do you have a cirrus, an alto cloud, cumulus cloud, different types of clouds, and then of course alto cirrus, alto cumulus, right? All the different types of clouds, they all behave differently, they all act differently. So this is extremely difficult to include as a parameter into the models. So that's one aspect, and how the researchers handle the water vapor parameter in their models will affect the projections. That's the first one. The second is aerosols. Right? We're familiar with the aerosol masking effect. That basically, when we burn the fossil fuel, we're adding tiny, tiny little particles that mask because they reflect sun energy back into space, so that the result is the aerosols have actually allowed the situation not to warm as much. So let's say, for example, instead of 1.6, if it weren't for aerosols, we could see something about 1.7, 1.8 degrees C increase. So now we have the paradox of, well, If we keep burning fossil fuels, we know we'll increase the temperatures. And if we don't burn fossil fuels, we now remove the aerosol masking effect, so the temperatures will increase. Burn fossil fuels and increase atmospheric temperature. Don't burn fossil fuels, the AME is removed, increase the temperature. Damned if you do, damned if you don't. And that's the dilemma that's being presented here. Well, how exactly do you model the aerosol masking effect? You have to look at, and that's going to depend, say, on the size of the particulate matter, on wind patterns. What area is affected? Is it local, regional, hemispheric, what have you? Another extremely difficult parameter to get a good handle on. So that study that I did, that I mentioned earlier, the one led by Christopher Paulson, they really took the time to, um, and they spent quite some time to get the models just right, to deal with the water vapor and the AME. It takes a lot of computing power. And there's been very few studies, been some, but very few studies. That study, I think, is some of the most comprehensive one that they did. They really accounted for those two parameters. So, how research is including, or not including, right? If you don't include the water vapor or the aerosol aspects, or how you include them in your models, will yield different projections of how much warming down the line. So that right there explains the range, the variability in the projected warming. But the projected warming is coming, and I looking at the research that I've looked at, when you take into account everything I have mentioned and laid out for you in this video, is locking us into a warming of 5C. And that's a conservative estimate, by the way. Now, if you go back to my recent ocean update video, I showed you the heat content. I showed you dramatic blue to this side, red to this side, and I put a big arrow on the graph about 1995, and I said that's the transition zone. That is the tipping point for the planet and for humans. Because before 1995, the oceans were able to sequester heat. And we see as we approach 1995, the ability and the amount it was sequestering was decreasing. And then what do we see on the other side of 1995? We see the ocean heat building up in the surface layers. And we see it what? Increasing ever more and more and more. In other words, it itself is exponentiating. The oceans are no longer able to sequester that heat to depth. It's now up there in the upper layers waiting to diffuse. It diffuses, it brings the CO2 with it. Everything else that I've mentioned, right? It's all going to contribute to this massive warming that will be occurring. So when you get the researchers who basically, you know, going, not playing the IPCC game, basically doing their own uh, research, and they create the equations, they run the models, they see the projections. This is where you start to see these at least greater than equal to 5C increase. And by the way, some of these papers project that CO2 could reach 1,000 parts per million. This is CO2 equivalent, could reach 1,000 parts per million by 2100. Humans came in, basically the planet was what, 285? We're now what, 421 or so? You talk about accelerations. And by the way, 1,000 ppms, Eocene levels. So when papers are able to really make a good accounting for water vapor and aerosols among all the other parameters put into the equations, this is the result, 5 to 11C. Most other models, especially IPCC, grossly underestimate. So this is why I made that assertion in that video of 5 to 11C. Take into account everything I've mentioned. You can go back, replay this video, write down all these parameters, all these aspects I've been mentioning. And I'm sure there's a few I haven't mentioned. But these will all contribute to an acceleration in the CO2 equivalent level, which will accelerate the temperature increase. We're now seeing talks of 2C by 2030. Well, then it'll be like 3C by 2040 and 4C by 2050. And all of a sudden, by 2080, it's up to, at least 5, if not 7 or 8 or 9. Because it's going to start accelerating. So I want to thank Heather for asking me to elaborate. I was happy to do so. I hope you found this video informative. I hope everyone found this video informative as to, as a breakdown as to why I made that assertion. And, I encourage you to look for my, and I'll put a video card in here. I encourage you to look at my lessons from the early Eocene video, where I discuss some of this as well. I made that video 2 years ago. It's even more dramatic 2 years on. So I said, thank you, Heather. I appreciate your interest and appreciate your question, and I hope you and everyone in my viewing audience found this video informative and helpful in understanding basically the dire situation that is taking place. So if you like the analyses that I present in my videos, if you like the content of my videos, I hope you will consider becoming part of the Patreon community. I have stopped monetization of my videos because it's annoying having the damn commercial interruption, and I would like to keep not monetizing the videos, but it would be really great if I get more of you folks joining the Patreon community. Like $3 a month, 75 cents a week. Really, I mean, 75 cents doesn't even buy you a subway ride in New York City. I don't think, right? What's so I hope that I can get more of you folks there to support this work that I do, and that will enable me to continue to bring contents such as this video and other videos I have done. So thank you for your time, and until next time, we'll talk soon.